Hello and welcome to the next module on linear block codes. We will start with a brief outline for today's talk. We will revisit systematic codes and talk about efficient decoding. We will look at something called as the Singleton Bound. Then we will move on to maximum distance codes. Finally, our main aim is to figure out how to perform error detection and correction. We will spend some time on that and we will look at some examples. So, this is the brief outline for today's talk. Let us see what we have already covered so far. We have introduced the linear block codes and talked about the notion of equivalent code. We then looked at generator matrix and the parity check matrix. We have already covered this, but we will quickly refresh our memories. So, we realize that there is a very efficient way to represent a linear block code using the notion of a generator matrix G. What it does is it takes in a vector 1 cross k, so k bit long or k symbol long input vector, and it is multiplied with G, which is k cross n, and you get a 1 cross n. So, that is pretty efficient. It is also a very concise way to represent your linear block code. So, G matrix is nothing but an n cross k matrix and it can generate q raised to power k code words. This will do away with the problem of putting it a very large lookup table. Then we looked at the notion of equivalent codes and we defined that two query codes are called equivalent if one can be obtained from other by permutations of the components and permutations of the position of the code words. And we said that we can define m code words in the form of a matrix which is m cross n, and then we can do two kinds of operations, operation 1 which pertains to permutations of the components and operation 2 which pertains to the permutation of the position of the code words. Any of them really does not change the distance properties of linear block code, and hence the error correcting capability is unaltered. Hence, these are the equivalent codes. We looked at the formal definition of equivalent code where two linear query codes are called equivalent codes if one can be obtained from one to the other using the generator matrices. And how do we do that? Multiplication of the components by non-zero scalar, permutations of the position of the code word. So, if two k cross n matrices generate equivalent linear codes of dimension n comma k over GFQ, then one of the matrices, one of the generator matrices can be obtained from the other using a sequence of operations given as follows. We can either permute the rows of the generator matrix, multiplication of a row by a non-scalar, or addition of a scalar multiplied rows with another, sum of two rows, sum of three rows replacing another row, permutation of columns, multiplication of any column by non-zero scalar, all of these operations in any sequence if can lead from one generator matrix to the other, then these two are called equivalent linear codes. So, we have already studied these so far. So, what is important is you can have any sequence of these operations. Then we got into the notion of systematic form. A generator matrix is reduced to its systematic form, which is also called a standard form, if it is represented as follows. The generator matrix G is partitioned into an identity matrix which is a k cross k matrix followed by a parity matrix P. So, I here is a k cross k identity matrix and P is the parity matrix whose dimension is k cross n minus k, thereby making this entire matrix k cross n. So, a generator matrix can be reduced to its systematic form of this type, and you can prove this, that this is basically the k rows of any generator matrix are linearly independent. We have established that. In fact, the rows of the generator matrix forms the basis vectors which generates the code words. So, hence performing elementary row operations and column operations, we can always find a K cross K identity matrix right here, and rest whatever remains is the parity matrix. So, clearly it is pretty easy to see that by simple row and column operations I can actually show that we have a rank K matrix, and here we have an identity matrix of size K cross K. So, this is a simple way to look at why each and every generator matrix can essentially be reduced to an equivalent systematic form. So, we have used these tools to come up with a systematic form. Now, question we ask ourselves is, generation is easy, we have done away with a lookup table, we can generate code words on the fly, but is it also possible to decode efficiently? That is to say, in order to check whether a received vector is indeed a valid code word, that indeed it has not undergone any errors, can we have an equally efficient method, and that could also be matrix based. So, the answer is a vehement yes. We have a matrix called a parity check matrix H for a given code. So, what does this parity check matrix do? Well, it does what its name suggests. Given a vector C, and if that vector C is a valid code word, then C H transpose should be a 0 vector for a valid code word. So, the parity check matrix can immediately tell you whether a code word has undergone error or not. So, take a valid code word, multiply with H transpose, and you should end up with a 0. Okay. Now, we know how a code word is generated. It is done so using a generator matrix C is equal to I information vector into G, and therefore, in general, if you replace the C by I into G, you get I G H transpose equal to 0, but this must be true for all valid code words, all information word. So, regardless of I, this must hold true, which forces us to put G H transpose equal to 0. So, we have a simple mechanism to find out H given G or G given H. So, if I ask you to represent a linear block code, you can give me the generator matrix, or equivalently you can give me the H matrix. We must observe that for a given G, H need not be unique. That is, we can have several options of H which will satisfy G H transpose equal to 0. So, the size of this uniquely important parity check matrix is n cross k cross n, and it is a simple method of detecting. Please note, it will only tell you whether an error has happened or not. It is not doing any job of correction so far. So, all you do is multiply the received vector with H transpose and wait for a non-zero vector. If you get a non-zero vector, you are happy because you can proclaim that no error has happened. On the other hand, if it gives a non-zero vector, that means something has gone wrong. But please note, this methodology succeeds only if the number of errors for which you have designed the parity check matrix is satisfied. However, if the number of errors in the code word exceeds the number of error for which the coding scheme is designed, then this will fail. So, you should be careful about this. You can end up having a 0 vector by performing CH transpose and still have a lot of errors in the code word. Now, how do we get this? So, we clearly know that any generator matrix G can be effectively represented as I and then partition and this parity matrix P. This P should not be confused with parity check matrix. This P is the parity matrix. It is sometimes also called coefficient matrix to avoid the confusion. So, the parity check matrix can now easily be defined as minus P transpose partitioned I, and you can easily check that G H transpose, if written in this form, is necessarily equal to 0. So, you can do a simple check. Here there is a transpose. So, you have I p here minus p transpose I is equal to 0, and this is an identity. So, you can easily first represent G in terms of its systematic form and then immediately obtain H from there. Now, we move forward and look at some properties of this parity check matrix H. So, the code C contains a non-zero code word of Hamming weight W or less if and only if a linearly dependent set of W columns of H exist. So, this is the statement, and what we do is consider any code word C belonging to the set capital C, and then let the weight of this code word C be W, which implies that they are W non-zero components, and clearly the length of this vector is n because it is a linear block code of block length n. Consequently, n minus W 0 components would exist in C. Okay, you partition it into the 0 component and non-zero components. Now, we must have CH transpose equal to 0. Okay. This capital C represents that all the vectors in this set when multiplied with H transpose should give you 0, including all the valid C1, C2, C3, all the valid code words. Now, we are considering any one particular code word with a weight W, that is W non-zero elements exist. So, what does this do? This product C H transpose 0 picks up the columns of H, and the linear combination of this column is equal to 0. Therefore, it obviously means that a non-zero code word of Hamming weight W or less if and only if a linearly dependent set of W columns of H exist. Okay. So, this process of multiplication is just picking out the W and showing them the linearly dependent W columns of H exist. Conversely, if H has W linearly independent columns, then a linear combination of at most W columns is 0. What is the practical use of this observation? Well, W has a very interesting connotation. The minimum W is called the minimum weight of the code, which is equal to the minimum distance of the code. W star is equal to D star. Consequently, by carefully observing the number of linearly dependent columns of H, we can make a statement about the W star. Right. So, W non-zero coefficients would define a code word of weight W or less that satisfies this condition. So, we can use this technique to figure out what is the minimum weight of a code. Now, we go back to our systematic code, and we have already seen that an n comma k systematic code is one in which the first k symbols of the code word of block length n are the information symbols themselves. Please remember, if we go back to the matrix representation, we have said that the generator matrix for a systematic code can be represented as an I, which is a k cross k, and a parity matrix P. So, whenever we are in the process of obtaining a code word C as a product of I into G, thanks to this identity matrix, the first k elements of this code word will definitely be I. And this n minus k will be the parity P. This is simply because of the construction of this G matrix in the systematic form. So, we come back to our slides and we say that in a systematic code, the first k symbols of the code word of block length n are the information symbols themselves, that is the uncoded vector, and the remainder n minus k are the parity symbols. Let us quickly look at an example. So, here is a code over GF3. It is an n comma k where n is 5 and k is equal to 2. So, it takes 2 symbols at a time. It is no longer a binary code. The elements can be 0, 1 and 2. So, it takes 2 symbols at a time and gives out a 5 symbol long code word. Here if you see, there are possible 9 code words in this table, and 00 has 00, 000, 01 has 01, 121 and so on and so forth. So, this is a 5,2 systematic code over GF3. If you do a careful observation, you will notice that the first 2 y2 k is equal to 2. So, the first k elements of the code word are the same as the uncoded symbols, and remainder are the parity n minus k, where n minus k 5 minus 2 is 3 in this case. So, why did we have the total number of code words as 9? Well, you will have q raised to the power k, q is equal to 3 because GFQ is GF3 here, and k is 2. So, 3 squared is 9, and each code word as we observed begins with the information symbol and has 3 parity symbols at the end. And a simple example was the information word for 01 has parity 121, making it the code word 01121. And clearly a generative matrix in the systematic form, which is also called the standard form, will generate a systematic code. Now, let us look at a very interesting and useful bound called the Singleton bound. What does it say? The minimum distance, and for us we always read the minimum distance as the minimum weight because we are in the domain of the linear block code. So, the minimum distance or the minimum weight of an n comma k linear code is bounded as d star equal to w star, upper bounded by, so less than or equal to n minus k plus 1. This is fairly interesting because so far n and k were supposed to be independent. I can have any k, I can have any n, only the rate meant k over n is the rate of the code, and you could always have any arbitrary choice of k and n provided n was greater than k. But please note, for linear block codes we have suddenly a constraint on the minimum distance. So, the maximum possible d star can never exceed n minus k plus 1. This is called a Singleton bound. So, if you just look at it, we have here the Singleton bound, and we have said d star is less than or equal to n minus k plus 1. So, please note, if you divide both sides by n, you have this normalized distance 1 minus k over n plus 1 over n. But if you see, this is nothing but the code rate of the code. So, you have the normalized minimum distance 1 minus r plus 1 over n. So, as you let n tend to a large number, that is, you are looking at a larger and larger block length, this quantity kind of tends to 0 and you are upper bounded by 1 minus the code rate R. But please note, R has a strong physical significance. It is actually the efficiency of the code. How much overhead bits or symbols are you sending, and R necessarily has to be as close as 1 as possible for practical codes. So, this puts in perspective that how a normalized D star is related to the code rate, which is the efficiency of the code, and it also tells us how both of them are contradictory requirements. On one side, I need R to tend to 1 because I do not want to put too many overhead symbols in my code word. So, R should touch 1. If I want to push that, then this quantity becomes closer and closer to 0. At the same time, I want this normalized D star not going to 0. So, on one hand I want to push my R, on the other hand I would like to increase my D star because D star has a direct implication to the error detection and error correction capability, as we will shortly see. So, we go back to our slide on Singleton Bound, and we make another observation that this holds for both binary and non-binary linear block codes. In fact, to prove this you only need the condition of linearity. How do we go about proving it? Well, we know that we can reduce all linear block codes to their equivalent systematic form. What does that mean? That G itself will be I partition P. Now, any systematic code will have one information symbol and n minus k parity symbols. Please recall that each of the rows of the G matrix is a valid code word and it forms the basis. But suddenly, how does my valid code word look? Well, if you go back and observe your systematic form, you will notice G represented as follows. And then you have your matrix. So, P11, P12 and so on and so forth. But please note that this is n minus k and this is k. This is also k. Now, we have established that each and every row is a valid code word, and since it is a linear block code, sum of any two code words is a valid code words. In fact, the moment we multiply I with G, I tells us which of those code words to pick and add them up. Fine. Now, if you just pick any one of the valid code words, you will have here at most n minus k. So, you can have this as all of them non-zero. In this case, the weight of this vector is n minus k plus 1, because in this row all of them are zeros except any one. This is true for all of these rows, and the linear combination you can always try that. So, no matter what you do, the minimum weight W star will always be less than or equal to n minus k provided all of them are non-zero plus 1. So, n minus k plus 1 is the upper bound and which is the Singleton bound. So, we go back to our slides and we observe that at most all the parity symbols can be non-zero, and therefore, the weight of any code word can be n minus k plus 1. Thus, no code word can exceed n minus k plus 1. So, now this is important because consequently we will have to relate the D star to some error correcting capability. So, let us talk about a maximum distance code in terms of the minimum distance, because minimum distance is a good property to have. We would like the code words to have as large minimum distances as possible. So, we look at the condition where D star is actually equal to n minus k plus 1, and all those codes that satisfy this condition, they are called maximum distance codes, right. So, this is coming directly from this inequality, and the moment we can reach the equality part of it, the code becomes a maximum distance code. Now, let us take one step further and talk about error detection and error correction, because that is what we set out to do. The basic objectives of the channel coding is to detect and correct errors when messages are transmitted over a noisy, unreliable channel. So, what does the noise do? Well, it does its job. It transforms some of the symbols or bits into something else. So, for binary it can flip the bits, for non-binary it can transform any of the symbols to be interpreted as any other symbol at the decoder. Now, just observe that if only one of the symbols in the transmitted code word is erroneous, then the received vector will be at a distance 1 from the original code word. What distance are we talking about? The Hamming distance. If there are t symbols which have been changed, altered, flipped, then the Hamming distance of the received vector is t. So, from now onwards we will start talking about a t error correcting code. That is, we wish that our code of block length n can correct t symbols in error. We will put that constraint and try to figure out what are the conditions to do so. So, first we look at the problem of error detection, because if we can detect, then only we can think about correcting it. So, an error will be detected as long as one of the code word does not completely transform into any other valid code word. Please note, we are in a space where n tuple represents a point in the space. So, let us look at another diagram here. So, we have this nice n dimensional space where any point in that space is a vector of length n, okay. And needless to say, you can have this n dimensional space represented. Now, you can have another point which is another n tuple, and the Hamming distance between them is the number of places one of the code words differs from the other code word. So, a code is a collection of code words, and suppose in my space, even though there are many points, only some of the points have been picked to be valid code words. Now, what happens when you transmit any one code word, say C1, and it gets one of the symbols in error? Well, the received vector is at a Hamming distance 1 from this code word. So, there are some possible vectors which are at a distance d equal to 1. But since we are saying that we would like to represent an error by t, we can say that t equal to 1 in this case. Suppose 2 bits or symbols get flipped, then there are another set of code words which is at now at a distance t is equal to 2. All of these code words are at t equal to 2. These code words are just not valid code words, they are vectors which are 2 places different with respect to original C1. And suppose my next tier of code words distance t is equal to 3 actually involves a C2. Suppose C2 is at a distance t is equal to 3 away. Then suppose C1 is in error such that 3 of the elements are interchanged and it resembles now C2, what I will receive is a vector C2 which is a valid code word. At the decoding side, I will have no way to figuring out whether C1 was sent and it had 3 errors or C2 was sent and it had no errors. So, the detection problem can only be solved if the number of errors are fewer than the minimum distance of the code. What is the minimum distance? Distance between the smallest distance between any 2 code words. Now, please note that a different combination of 3 errors could have happened and what I receive is this vector or this vector. These are not valid code words. So, still I can detect them to be in error. But if my luck is bad and my C1 gets transformed to C2 with 3, then there is no way I can detect. So, the worst case I would like to say that the number of errors to detect. So, I can detect maximum d star minus 1. I cannot detect d star errors because one code word will become another code word and there will be no way to finding out. So, we go back to our slides and we look at that there is at least one error pattern of weight d star which will not be detected. Which is the one? This corresponds to the 2 code words that are the closest and one will get transformed to the other code word. It may be however possible that some error patterns of weight d star or more are indeed detected because you do not transform one valid code word to another valid code word. However, the ambiguity remains, but all error patterns of weight d star will not be detected. Some will get transformed into another one. So, let us look at a quick example. Let us look at this simple toy example of a repetition code. N is equal to 3, k is equal to 1 and the minimum distance is 3. There are only 2 code words 0 0 0 and 1 1 1. Minimum distance is 3. So, what does it mean? Any error pattern of weight 2 or 1 can be detected. So, how many are there? Well, 0 1 1, 1 0 1, 1 1 0, so and so forth, patterns of weight 2, patterns of weight 1, all of these can be detected. That is to say, if I transmit 0 0 0 and either 1 or 2 errors happen, I can always say, look, I did not receive 0 0 0 or 1 1 1, so my flag goes up and some error has happened. But if 3 errors occur, d star is equal to 3, then 0 0 0 becomes 1 1 1. I really do not know whether to be happy or sad because 1 1 1 is a valid code word. So, if you have another example where C2 is these 3 code with d star is equal to 1, well, if d star is equal to 1, we do not know whether it can detect errors or not. The error pattern of 0 1 0 of weight 1 can be detected by this code, because any 1 when transformed will be detected, because it is not one of the valid code words. But suppose 1 0 0 happens, so 0 0 1 will become 1 0 1, and there is no way I can detect what was sent. So now we would like to look at the collection part, the decoding part. So we would like to ensure that the received word, which has t errors or at most t errors, is closest to the original word, code word, and at the same time farther from any other code words. Okay. So we want to have unambiguous decoding. So what I want to do is the minimum distance, which is the relationship between the 2 code words which are closest to each other, that separation should be greater than 2t plus 1. Well, it is easy to visualize. Let us have our coordinate system in place, and I have just shown 3, but it is an n dimensional space, and I can always put a point in the space which represents code word C1, and there will be a decoding sphere around it which is of the size radius t. It means within this circle there are many points which are at a Hamming distance t or less. Okay. So just remove that axis and just focus on C1 and C2. All right. So we are trying to figure out what is the best way, what is the constraint we can put to ensure that I can correct t errors. So we draw a circle around C1, and there are many points inside this circle which are at a Hamming distance t or less. Whoever is sitting on the circle's circumference is exactly at a Hamming distance t. Rest are closer to or farther away, but definitely less than t. But the worst case is that this guy is sitting on t. Now we can have non-overlapping spheres such that C1 and C2 do not overlap in terms of their decoding spheres. But if t touches, the circumference of these 2 circles touch each other and a code word lies on this, then we do not know, because it is equidistant from C1 or C2, and we cannot do the nearest neighbor decoding. Otherwise, if I have any valid code word sitting inside this sphere, then if this vector is received, most likely C1 was transmitted, not C2. So I can, any code word, any vector sitting inside this sphere will be mapped back to C1, and therefore this is the decoding sphere for C1. Similarly, this is the decoding sphere of C2. Any received vector inside C2 will be mapped back to C2. But to ensure that in the pathetic case when the circumferences touch, then any code word sitting on, or any vector sitting on the circumference will be, it will be ambiguous whether to put on to C1 or C2. We need a separation of 1. It can only be an integer, so it is 2t plus 1. So we have to make sure that the code words are separated to greater than 2t plus 1 or 2t greater than or equal to 2t plus 1 if I want to ensure that t errors are indeed corrected. So what does it mean? Well, every query vector of length n can be represented as a point in the space, and every code word is depicted as a point, as we saw last time, and the sphere contains all the valid vectors within it of the distance t or less. And we established that d star should necessarily be greater than or equal to 2t plus 1, then the spheres will never intersect, and nearest neighbor decoding can indeed happen. So, let us look at another simple example. Well, k is equal to 2, n is equal to 5, and we can find out very quickly that the minimum weight and minimum distance of this code is indeed 2. Suppose this 1 1 1 1 1 vector was transmitted, but one bit got flipped. So, what we received was 1 1 1 1 0. So, the fifth component is in error. So, you can find out the distance, the Hamming distance of this received vector with each one of the 4 code words, and I find that the distance is least with respect to 1 1 1 1. So, in the code space, the received vector is closest to 1 1 1 1 1 than any other code word, and hence the nearest neighbor decoding tells me that okay, not only did you make an error, you have a fair chance of correcting it, and the real code word that was transmitted was 1 1 1 1 1, and you have been able to recover from the error. So, we applied this nearest neighbor decoding. Now, please note that D star is 2. So, in principle we should not be able to correct a single error, because D star should be greater than or equal to 2 t plus 1. Here t is 1. So, D star should be at least 3 to correct one error, but we have been able to correct one error. But this is not true in general. So, some special cases you can correct. The point of this example is to show that D star greater than 2 t plus 1 ensures all sad pathetic cases are also covered. You will never make a mistake, you will always be able to detect and correct t errors. So, for certain scenarios it is possible to correct errors even if D star is less than 2 t plus 1, but in many cases a single error correction may not be possible. For example, if 0 0 0 0 0 was sent and we make one error, t is equal to 1 again, second component is an error, I now again find the distance with all of them, and suddenly I am in a dilemma, because two of the valid code words are equidistant from my received vector. What do? I need to guess, and I can always toss a fair coin, because any one could be valid and I have no way of being sure which one to suggest. This brings us to this definition of a complete and incomplete decoder. That example motivates this definition. An incomplete decoder decodes only those received code words that are clearly closest to one of the code words. Okay? In case of ambiguity, just like we saw in the previous example, the decoder declares that the received word is unrecognizable and it raises its hands. Then the receiver then says, look, error is detected, can't correct, please retransmit. Okay? It can also do this automatic repeat request, the ARQ. On the other hand, we can be adamant, we can say a complete decoder is one which definitely decodes every received word, whether there is an ambiguity or not. Even if it has to make a guess, it will do so, but it will give you an answer, it will never ask for a retransmission. So, let us look at one final example, a practical example. This is the ISBN or the International Standard Book number, which is present behind every book that you see. It is a linear block code over GF11. Please note, this is a prime number, so GF11 exists, and the block length is 10. Now ISBN 13 is also available, but this example is for ISBN 10, where n is the block length. How do we represent this GF11? Because GF11 must have 11 symbols, including 0 and 1. So, we have 0, 1, 2, 3, 4, 9, and I should have the 10, but 10 can be confused as 1 followed by a 0 and 1 and 0s are already valid. So, we put in x. Okay. So, x represents 10. So, your code word, whatever is written behind every book, will have either 10 or 13 symbol long code words. Okay. And the ISBN satisfies the following condition: 10 minus I into Ci, where I is the component, ith component, I is equal to 0 to 9, because there are total 10 elements in the code word, should be 0, provided it is calculated mod 11. Of course, the arithmetic has to be mod 11 because it is a code over GF 11. So, if you have this condition satisfied, then you can declare whether an ISBN is a valid ISBN or not. Okay. So, let us look at a quick example. Now, let us consider this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 symbol long ISBN. Okay. We can do a quick check on this ISBN and we can apply the formula that we saw in the previous slide, the summation, and you multiply the first one with, so the first number, second number with 10 minus I. So, 10 into the first number 0, 9 into 0, 8 into 7, and so forth. You can go right up to the last one, 1 into 7, and you take modulo 11 and you end up having a 0. So, you can carefully observe this and say that yes, indeed it is a valid ISBN. Okay. You can do this check. So, what is the use of this? I mean, where are we doing error correction here? This is supposed to be error detecting, error correcting code. So, let us look at what we can actually get out of it. But before that, we must look at the property of an ISBN. So, an ISBN is a linear block code, which means that the all 0 code word is a valid code word, and a sum of any two code words is also a valid code word. So, the moment you throw a linear block code at me, I first find the D star. I have to find out the minimum distance, because then I will know the error detecting and error correcting capability. So, one of the ways is either to list out all of the code words. Well, you will need a lot of good luck and compute power to do so, or we can play a smart trick. We focus hard enough and come up with another seemingly valid ISBN. So, you can check that this number also satisfies the constraint for an ISBN code. So, it is a valid ISBN code. So, I have identified the all 0 and this one, and of course, the minimum distance will be 2. So, the ISBN code has D star is equal to 2. So, it can detect, but in principle it should not be able to correct a single error, because error correction requires D star to be 3 for a single error correction. Okay. So, are we looking at a useless code? Theoretically, it cannot correct any errors and can only detect a single error. So far so good, but can we extract more out of it? Let us look at an example. So, we put another valid ISBN. You can satisfy yourself that this is a valid ISBN, but you know books, we work with pens, there are moths around, and you can have an ink pen which is leaky and you splash some ink. So, one of the digits is blotted or smudged. So, we have no clue what it was. The moth could have eaten it, or ink has dropped on it, and I need to know whether this is a valid ISBN or not. So, this is a problem not of error detection. Clearly, the error is there, I can see that error, but can I correct, can I recover from it, can I guess what is this? So, I model this ink blot as my error E. Okay. So, what we do is we again apply that condition, and that was an equation one equation, one unknown is easy to solve, and little bit of math and it tells me that E is 2. So, I have been able to give you the value of E. Not only did I detect the error, I corrected the error. What is this? This is an error and I have corrected it. E is 2. And how did I do it? Because theoretically I should not be able to correct an error. Well, the answer is we have been able to correct a single error simply because we know the location of the error. In linear block code, you do not even know the location. So, you can do much better if you can know the location of the error. That is an additional information which can help you recover from errors. So, with that we come to the end of this lecture. Let us summarize what we have looked at in this past 1 hour. We have looked at systematic codes, we have understood how they are written, what is the purpose, what is the advantage of putting codes in a systematic form. We looked at efficient decoding, then we observed what is a singleton bound and how it can lead to the definition of a maximum distance code. We then looked at the notion of error detection and correction, and finally we looked at a very practical example, the ISBN. With that we come to the end of this lecture.